Good morning, guys. Those who are online, are you able to hear me? Students who are online, are you able to hear me? So can someone speak, please? Says host is not available to unmute. Okay, let me check. Shubham, can you try to speak now? Are you speaking? Can you speak now?
Yes, sir, I can speak.
Yeah, I will speak. Okay. So I hope you all are able to see the screen also, right? Yeah, those who are online, are you able to see the screen?
Yes, sir.
Yes, sir.
Okay, we'll get started. Okay. So shall we go on to the next one? As discussed in the previous class, we'll start with the fourth chapter, that is moving charges and magnetism. Okay. So let's recollect one concept. Okay, let's recollect the concepts that we have discussed till now. First, we discussed about electrostatics. What does that speak of? So first we spoke about electrostatics. It speaks about the static charges. What do you mean by that? So we were mostly concerned about what happens when charges are present. So what do they generally do? So if there is another charge, it will start exerting a force. If there is only one charge, it will start creating a field around. So these are the only two concepts that were there. Okay. The next question that we thought of is, if it is able to generate a field, does it have some energy associated with it? That's what the next chapter we were mostly concerned about. Right? If you talk about a single charge, will it be able to do some work on some other charge, the test charge which is kept closer to it, right? So that's what we called it as electrostatic potential energy and electrostatic potential. And our topic was mostly restricted to those concepts. Then at a later point in the chapter, we started seeing how the electrostatic potential and fields are related. E is equal to minus dV by dr. If you recollect, that is the expression, right? After that, what did we see? Then we thought of what will happen when the electric charges are put in motion. So when they are put into motion, what happened? It started constituting some current. So everywhere it starts with charges, right? And that current could do what? Okay, how could the current be generated? By applying some potential difference. When you apply that potential difference, the work was done by the electric field on the charges present inside the conductor, and they started moving inside, right? So this is how the story is coming. Now the fourth chapter also has something to do with charge. What is it? So you're saying it is moving charges and magnetism. What do we mean by that? So what do we mean? Current can be or what? Current and magnetism are related. If you recollect, right, this is a chapter from your 10th standard where you learned under the name called as magnetic effects of electric current. So it's the same thing. Okay. The only difference is there you would have only drawn the magnetic field lines and all other stuff. Here we'll be concerned about why they are actually forming and what will be the mathematical expression for those magnetic fields which are generated due to current carrying conductors. Okay. So if you ask me, right, this chapter, I will say it is broken into, I can say it's 3 parts, or I can say 2 parts on a major level. First is, we will take a current carrying conductor, listen to this carefully. We'll take a current carrying conductor, and due to the current carrying conductor, we will see what is the magnetism generated. As the name of the chapter suggests, moving charges and magnetism means charges which are in motion can generate magnetism. That is what the topic is. Okay. The second question is, you already have a charge or you have a current carrying conductor in your hand. What will happen if you take those charges or current carrying conductors and put it in some external magnetic field? What will happen to them? So this is how the chapter is broken into 2 parts, but we'll read it as a combined part. Okay. In your text, I'm not going to follow the textbook order for this chapter because they have slightly jumbled things, which I don't want. I'll be taking the second part first and the first part next so that you will have a continuity. Is that clear? So are you able to understand the context of this chapter? So what do we say? How moving charges are able to generate magnetism. If you see the next chapter, right? Next chapter is called Magnetism and Its Matter. So here also you're talking about magnetism. There also you talk about magnetism only. But what is the difference? Here you talk about magnetism generated by current carrying conductors. Means as long as the current is there in the conductor, you can observe magnetism. As soon as it is lost, magnetism is also lost. Means this wire is there, right? So you're able to see this. So you're able to see this wire, right? It is switched on and the current is passing through this wires. If you try to take a magnetic substance, when I say magnetic substance, it can be some iron nail or something. You generally know what happens, right? You take an iron nail and place it closer to a magnet, what will happen to it? It will attract, right? So it is because of the magnetic properties exhibited by that magnet. Okay. If I take the same iron nail and place it here, do you think it will get attracted? In this scenario, do you think it will get attracted? I'm able to touch the wire confidently. I'm saying current is flowing, but I'm touching it because I have an insulation on top of it. But inside wires are there, right? So inside wires will also have insulation. And inside that, what will you have? You will have thin copper wires, right? When you pass more amount of current through it and take some iron nail and place it closer to it, right? It will get attracted. Okay. So that was the first observation that was done. So that is where, so till then what people were thinking is current, electricity is something different, magnetism is something different. But later point only they came to know that these two are also interrelated concepts. So why I'm saying interrelated is because just because I am saying current carrying conductors can generate magnetism, it doesn't mean the vice versa is not possible. You can use magnetism to generate current also. That is called as electromagnetic induction. Okay, so that we'll be seeing in the 6th chapter. So to set a context, right, in this chapter, we are only going to be concerned about 2 things. If charge is there, if the charge is in motion, then you say current is there. Or you can directly have a current carrying conductor. If these two are there, what is the amount of magnetism generated by those kind of elements? And the second part is you already have magnetism. So what do I mean by you already have magnetism is, see, for example, I take this bunch of keys. If I release it here, if I remove my hand, what is going to happen to it? Obviously, it is going to fall down. Why is it going? Because we have around us something called as gravitational field, and the gravitational field is pulling this mass towards the center of the earth. That's what we say. So in a similar way, instead of this room being full of gravitational field, had it been full of magnetic field, And instead of this being a mass, had it been a charge, then we will see what will happen to these charges in the presence of magnetic field in the second part of the chapter. So having said this, are we ready to get started? Yes? Right. So first write down the heading moving charges and magnetism. So you're able to see a scientist here, Hans Christian Oyster. So he was the first person who has observed that magnetism can be generated from electricity. So before that, as I told you, people were thinking that they both were from different branches, but it's not the fact. So he was the first one who proposed it, okay, stating that moving charges can generate magnetism. So after being said, the next important question that got raised is, if at all it is able to generate magnetism, how will you calculate the magnitude of those magnetic fields that are getting generated? So we are going to get into the first context of this chapter, which is called as, please write it down. It's called as Biot Savard's law. So there were two scientists named Biot and Savard. Okay, these two scientists put together, what they did is they gave a mathematical expression for the value of magnetic field that you get generated. Okay, so I'll give you an example. See, let's say I have a conductor like this. Okay, and let's say current is flowing in this conductor in the upward direction. Right. So can I say that this current carrying conductor is made up of small elements? Those elements put together, only we call it as a full conductor. Let's say this element has a thickness of, or a small length of dl. Okay. Then I have a point P which is at a distance r from this current carrying conductor. Sorry, current carrying element. So I label the parts again. That whole S-shaped curve is a current carrying what? So it is a current carrying conductor. That is the first part. This dl is also current carrying something, but what is it? It is called current carrying element because it's a small piece. Okay, the point P is the place where you are trying to calculate the field. From dl to point P, the distance is r. Okay. Now, if I say the angle between the current carrying element and r is theta. Okay. So this theta, remember, you need to be very careful when you're choosing it. I'll tell you how to choose it. But as of now, mark it. Okay. If I call this as theta, then there is something called dB. So generally the term d comes before any physical quantity. You call it as a differential coefficient. So differential coefficients are used to calculate smaller values. Okay. So dB is called as the small, or I'll call it like this, magnetic field due to the current carrying element. So it is called as the magnetic field due to the current carrying element. Okay. So this magnetic field due to the current carrying element is observed to be directly proportional to the value of current that is flowing through the conductor. Do you remember this by any chance? So if you have a current carrying conductor and I give you a task that increase the strength of its magnetism, what is the first thing you will try to do? You will try to increase the value of current through it. Correct? Secondly, I'll make a small change here. dB is observed to be directly proportional to I into dl. Okay. So it is proportional to I into dl, and dB is directly proportional to sine of the angle between the current carrying element, sine of the angle between the current carrying element and the distance vector. Okay, sine theta, where theta is what? Angle between current carrying element and r vector. Okay, and the next one is dB is observed to be inversely proportional to r square. It is observed to be inversely proportional to r square. Are you able to understand this point? So what does that r stand for? R is the distance between the current carrying element and the point where you're trying to calculate. Are these three things clear? Right. Now our job is to combine everything and give a final expression. So there is no proof for this thing. Don't worry about it. You just have to understand this concept. So dB is directly proportional to ideal sine theta divided by r square. Okay. Now, if I remove the proportionality symbol, what am I going to get? dB will be equal to mu naught divided by 4 pi into ideal sine theta divided by r square. Okay. So this is going to be the final expression for the magnetic field due to a current carrying element. It is not the value of the total magnetic field always. Remember, Biot Savard law never spoke about the total magnetic field due to the whole conductor. It spoke only about a small element taken on the conductor. So the expression always should have the dB. Don't make a mistake of writing it as B. Whole context will change. So mu naught divided by 4 pi into ideal sine theta divided by r square. Okay, this is the expression. Now, the next important question that arises is, okay, you have written an expression for the magnetic field due to that small element. The second question is, at the point P, does this magnetic field have a direction associated with it? Or is it a scalar quantity? So what is the answer? It has direction. So how do you find the direction generally? Okay, so every time you not have a compass, right? Is there any other way? So you use something called as right hand thumb rule. I'll come to that context. I'm sure that you at least remember those terms, right? So what are those things? We'll see it one by one. But from the basics of your 10th standard, I'm clear that you know that magnetic field has direction associated with it. When it has direction associated with it, it is our job to write this expression dB, which is in this cloud, written in the form of a scalar value. Now I have to write the same thing in the form of a vector and understand how to find the direction. So observe. If I write the same dB as a vector, right, it is written like this. Mu naught divided by 4 pi. What is that mu naught? I'll tell you. Wait for it. Mu naught divided by 4 pi into, see, generally whenever sine theta comes, right, what is the product you do between vectors to generate sine theta? You do cross product or vector product, right? So I'm able to understand that this ideal should be written in terms of cross product. So if I have to write something in terms of cross product, I need two vectors. Now I'm looking at the numerator. Mu naught is a constant. It's not a vector. It's a scalar quantity. I, is it a scalar or a vector? Current. Current is a scalar quantity. What about dl? dl, you can make it as vector quantity if you wish to, where dl will be assigned the direction in which the current is flowing. So dl is a vector quantity. Okay, but I have only one vector quantity in the numerator. So what is the other vector quantity I am able to see from the diagram? So what I need to do is I need to bring that r in the numerator. Okay, so for that what I will do is this mu naught, listen to this carefully, mu naught divided by 4 pi into ideal into r sine theta divided by r cube, is that right? Is that clear? Right. So what I did is I multiplied and divided with r. Then this dl is one vector quantity I am able to see, r is one vector quantity I am able to see. Now I need to write them as a cross product between dl and r vector. This I am clear now. But again, with cross product, I have another challenge. What is it? I need to know which one should come before cross and which one should come after cross. Why? Because A cross B is not the same as B cross A. If I swap and write it, just because I have ideal sin r sin theta, if I write it as dl vector cross r vector without knowing the actual context of it, means the dl vector cross r vector should satisfy my so-called right-hand thumb rule. If that should happen, then I need to choose the right direction of it. Okay, so I'll tell you what it is. I is a scalar quantity, don't disturb it. Here, you should write it as dl vector cross r vector only. Why is it so? I'll give you a justification for it. Divided by r cube. Okay. This is an other important expression. So what I want you to observe here is, can you tell me the difference between the first cloud and the second cloud? What is the important difference you are able to find between both? One is sin theta is eliminated, that is in the numerator. Look at the denominators. When I write it as scalar quantity, the denominator is r square, whereas when I write it as vector quantity, the denominator is r cube. Provided I write it as dl vector cross r vector. Purida. Okay, that these are the two important points. Make a note of it. Clear? Guys, so online, are you clear?
Yes, sir.
Yes, sir.
So now listen. Having said all these things, I'm going to explain two things in parallel now. Listen to this very carefully. Okay. One is something related to this chapter, one is something related to vectors. So with respect to this chapter, I'm going to explain you what is right hand thumb rule. Okay, you can call it as RHTR. Right hand thumb rule. Better. Now, for this right hand thumb rule, what am I supposed to do? You take the right hand. Okay, name itself says right hand, but I need to take the thumb of my right hand and do something. Because there are two rules, okay, you will get confused between these two. One is right hand thumb rule, and second is called as Fleming's right hand. You know the difference between both? So right hand thumb rule, you need to use only your thumb and the remaining fingers. Whereas for Fleming's right hand rule, you need to use the first three fingers. Okay, any idea where it is used? That is left, that is left. No, why do you use it? Force left hand. To find the direction of induced current, we use the right hand, Fleming's right hand rule, which we'll see it in the 6th chapter. So in this chapter, we'll be discussing two rules. One is the right hand thumb rule, and the second is the Fleming's left hand rule, which is used to calculate the direction of force. I told you about the charged particle in magnetic field, right? That time it will experience force, we'll use our left hand rule. So, sorry, Fleming's left hand rule. Clear? Now, can somebody state this? Can somebody state right hand thumb rule? No, I didn't get you. Can you repeat it? Direction of electric current. Okay. Magnetic field. Correct. So please make a note of it. Extend thumb of your right hand in the, so underline the word right hand. Okay, extend the thumb of your right hand in the direction of whom? The direction of electric current. And what are we supposed to do with the remaining fingers? Curl fingers as if you're doing what? You are holding the conductor. As if you're holding the conductor. Then the direction in which fingers are folded gives what? Direction of magnetic field. Correct? Huh? Okay. Now let's check this. Okay, now we need to validate two things. One is this right hand thumb rule, and the second is understand why we wrote it as DL vector cross R. Why not R cross D? Let's try to check it. So if I take this as the conductor, this side represents the direction of current. The same as the one I did that I drew here. Except only thing is here it is bent, here it is straight current carrying conductor. Okay. So if this is the direction of current, what does right hand thumb rule state? Look at your notes and tell me. Take your right hand, extend the thumb of your right hand in the direction of current, and curl your fingers as if you're going to hold it. When you hold it, right, this is how the diagram is in your textbook. Sorry, in your notes. Right, you keep the thumb like this. When you curl the fingers at point P, are your fingers going and touching the paper, or are they coming out of paper? They are going and touching the paper. So touching the paper means the magnetic field is going into the plane. So when something is into the plane, you put an into mark and a circle around it. Okay. Similarly, had I taken this point P on the left hand side, had I taken a point P on the left hand side, if I called it as P dash, then observe. So I want to tell you one important point. So instead of current carrying conductor, if you had a linear charge conductor, a linearly charged conductor like this, at this point, the electric field would have been away from it. At this point, also the electric field would have been away from it. Accepted? Right. But what are we trying to talk about here? Are we trying to talk about electric field in the case of current carrying conductor? No, we are calculating the magnetic field. So at point P, if the magnetic field is inside, one point that you need to note is on either side of the conductor, the magnetic fields will always be in opposite directions, unlike electric field. Okay, means whichever side is comfortable for you, you can find the magnetic field on that particular side. by default on the other side of the conductor, it will be exactly in the opposite direction. Why is it so? Because this is how the conductor is, right? You place your thumb here and you curl the fingers. At point B, it is going into the plane, and at point P dash, it is coming out of the plane. For out of the plane, you put a dot and a circle around it. I repeat, for into the plane, you put an X mark and a circle around it. And for out of the plane, you put a dot and a circle around it. Okay. Listen to this point alone. This into mark and dot, people think that it is applicable only for magnetic field. No, it is just a notation. Okay, so this into mark, if you're putting it and a circle around it, you're trying to tell the reader that some physical quantity is into the plane. It can be magnetic field or sometimes it can be current also. So don't have a strict fix in your mind stating that this is happening only for magnetic field. Am I clear with that point? Okay, first wipe out that, because there is one concept called a solenoid. There you put an into mark and a dot around it for current. Okay, so at this point itself, erase the fact that it is applicable only for magnetic field. Okay. Now we are supposed to validate this dl vector cross r vector. So I wrote the magnetic field dB at which point the dB vector which I have written in the second cloud. It is written for the point P. Correct? So at point P, what did we find out? The magnetic field is into the plane. Adum correct? So that we validated using right hand thumb rule. Now we need to validate the same thing using vectors also. Okay, for that I need to just slightly touch upon the vector product. I think I've already explained this in the first chapter when I explained torque. I'm not sure if you guys remember. Vector product of two vectors. So vector product can be between three vectors also. We'll start with two. If I take this as A vector, this as B vector. So if I write A vector cross B vector, what do I mean by that? If I write something as A vector cross B vector, what do I mean by that? From A vector, I need to take a turn towards the second vector in the shortest direction possible. So please make a note of it. So to make it more generic, right, instead of A cross B, we will write it as first vector cross second vector. Means the meaning of it is, from the first vector, you need to take a turn towards the second vector in shortest, not small, shortest direction possible. So please make a note of it, write it. So first vector cross second vector means take a turn from the first vector towards the second vector in the shortest direction possible. Clear? In this case, from A vector to B vector, if I need to take a turn, what is the shortest direction that I'm able to see? Is it clockwise or anti-clockwise? Obviously clockwise. Okay. When this is the case, now again, you need to take the help of your right hand. Okay, this we call it as screw rule. Okay, you take the help of your right hand. This time you will be doing the reverse. You will first curl the fingers and then extend the thumb. So curl the fingers of your right hand in the direction of A vector cross B vector. Okay, I repeat it. See, curl the fingers from A vector to B vector and extend your thumb. That will give you the direction of magnetic field. That will give you the direction of A cross B's resultant at that point. So how is it? A cross B in this case is into the plane. Okay. Similarly, what would have happened to B vector cross A vector? It would be out of the plane. Okay, that is the most important point we need to have. So I think I've given you an example for it, which is your water bottle cap. If you recollect it, if you want this cap to come towards you, means if you need to open this bottle, by default, what will you do? You turn it from the top, if you see, you turn it in the anti-clockwise. So anything anti-clockwise will always be towards you. Anything which is clockwise will always be away from you. The same thing is happening here. When something is clockwise, it is away from you. When something is anti-clockwise, B cross A is upward, right? It is towards you. Are you able to understand? So that is why I called it as screw rule, because all the screws in this world have a fixed direction. You can never find a screw where you want to close and you will turn, it in anti-clockwise direction. That is how manufacturing companies itself will work. Are you able to understand? Now, having said this, can you validate this dl vector cross r vector for our example that we have taken? Can you validate dl vector cross r vector? Tell me. So I is in the upward direction. Ideally, I told you dl will take the direction of current itself. Ideal is in this direction. R is in this direction. So dl vector cross r vector means dl should go towards r. When you see it from your side, in which direction should it rotate? So I'll take it like this. This is the side in which you are there. Current, this is r vector. From I need to go to r. What is the direction? Clockwise. Clockwise means, is it away from you or towards you? Away from you. So it is going to be in this direction. So magnetic field is into the plane. That is the reason why I wrote it as dl vector cross r vector. Okay. And one important point I would like to mention here is, though we have right hand thumb rule, I will not use that right hand thumb rule in every context. I will only go with vectors because vectors will not cheat us. It's a direct mathematical expression. I will only solve every problem or every derivation in this using only cross product of vectors. So I need you to have the utmost clarity on it. Is it clear? Is everything clear? Okay. So this is what is Biot Savard law. Now coming to this mu naught. This mu naught is called as permeability of free space. Please write it down. It's called permeability of free space. What do you mean by permeability? The extent to which the medium allows the magnetism to exist in it. The extent to which the medium allows magnetism to exist in it. Okay. So throughout physics, from whatever discussion we had till now, we saw two important constants of this sort. One is permeability and the second is permittivity. Remember, there is a reason why we are studying these two, because these two concepts put together give rise to a concept called as electromagnetic waves, which is nothing but light. Visible light is one of the electromagnetic waves, right? One of the forms of it. So when you say that, we will be relating all these concepts at that point. In the 8th chapter, we'll try to take everything and combine it. So you need to know what the significance they show. Okay. So mu naught divided by 4 pi is equal to 10 power minus 7. This is the value. Okay. But I want you to find out the unit of this and tell me. For that, can you find out the unit of this and tell me? You already have the knowledge of units and measurements. For that, you need to know what is the SI unit for magnetic field. What is the SI unit of magnetic field? Any idea? It's the name of a scientist. Very famous scientist. Oyster. It was very famous. Oyster make down a theory. Must put a company for Tesla. Did someone say Tesla? I didn't hear. It's Tesla. Ampere is for current. How is it ampere? You mean to say current per unit length is? Oh, you're saying for mu naught by 4 pi. It would have been ampere per meter had the value of mu naught by 4 pi had no units. I'm asking you to find the unit of it. So mu naught by 4 pi. So magnetic field is measured in Tesla. Remaining things you know. Tesla. So it is Tesla meter per ampere. Is it clear? Okay, so it is 10 power minus 7 Tesla meter per ampere, and in most of the problems you will not need mu naught by 4 pi, you need only mu naught. So if they ask for mu naught, what will you do? Take the 4 pi to the other side. So mu naught will be equal to 4 pi into 10 power minus 7 of that time of those units, Tesla meter per ampere. Is that clear? Okay. Having said this, are we ready to go for the application of it? It's a slightly tougher one. I want you all to concentrate as much as possible. It involves a little bit of mathematics also, so concentrate. So write down the heading. I'll call it as applications of Biot Savard law. Okay. So the first application that we are going to see is magnetic field due to a straight current carrying conductor of finite length. So magnetic field due to a straight current carrying conductor of finite length. Is it clear? Let's see. What do I mean by that? Okay. So I have a current carrying conductor. Let's say its length is capital L for the time being. Okay. And let's say the current in this conductor is in the upward direction. So I'm interested to calculate the magnetic field due to this kind of a system at a point P, okay, which is at a distance A from the current carrying conductor. Okay. Is it clear? Now the question is, I need to take the help of Biot-Savart law to apply this. So for me to apply Biot-Savart law, first thing that I need to recollect is, Biot-Savart law never speaks about the magnetic field due to the whole conductor. It speaks only about an element. So first thing which is missing here, which I need to consider is what? An element. I need to take an element. Now the next question is, where do I take it? So I'm free to choose. Okay. So I will take this as the current carrying element. But remember, right, whenever you're doing something with respect to differential coefficient, the rule in physics is you should always have a reference point and start doing it. Because wherever differential coefficient is there, you can eliminate the differential coefficient by doing what? When can you eliminate D? Only when you do the reverse process, that is antiderivative or integration, right? So if I take this point as O, okay, that is a reference point. From this O, I'm saying at a distance small l, I have a small current carrying element dl. What is the next other thing that I need? I need R. So can I say in this case, R is nothing but A? Correct? That is where you're doing a mistake. What is that R I told you? The distance from the current carrying element to the point P. It is not the distance from the current carrying conductor to the point P. Okay, concentrate. From DL, if I take this distance as R, okay, then I'll be able to use it in the formula. What is the other parameter I need? There are three parameters. Angle between them. So when you take the angle between them, you need to take the angle between the current carrying element and R. So it is going to be this thing. Accepted. Okay, I just want to see out of context for me in this case, but I want to tell this point. Had I taken the current carrying conductor's current to be in this direction, okay, had I taken the same point P and distance A, I take this as DL. This is there, right? Now I'll give you two options, alpha and beta, which is right, which is the right one for the angle between the current carrying element and the conductor and the distance. So it is beta. Why? because the current is in the downward direction. So from the current carrying element, you need to take it to R. Okay. So this is a very, very, very important point. Very rarely they ask in problems also. What they will give us, they'll give this kind of a scenario. They'll give you the value of alpha as something, and they'll ask you to find the magnetic field. See, fortunately, sine theta and sine 180 minus theta are the same. You'll be safe, provided it's a straight current carrying conductor. But if there's something else, you'll get stuck. Am I clear, guys? Can I rub this? The second diagram? Those who are online are able to understand?
Yes, sir.
Yes, sir.
Yeah. I'm just removing this. Now listen to this carefully, okay? Now, I'm going to write the expression dB is equal to, tell me, mu naught by 4 pi is a constant, I is a constant, dl is there into sine theta divided by r square. I'm going with scalar quantity. I don't need vectors here because I'll use right hand thumb rule to understand. Right? Ideal sine theta by r square. So what did I say? If you have to eliminate the d for b, that is db is there. If I want to make it as b, I need to integrate it. So can I start integrating on both the sides? Right? You can't do that. Reason being, if you need to integrate something, see, there's a major point which many people miss. What is the answer? What is the integral of sin x? Minus cos x. Correct? Accepted?
Sir, there is no dx.
Somebody told. Shubham, is that you?
No, sir.
Yeah. Who told? Who told that there is no dx?
Giridhar, sir.
Good. So integral of sin x means you should ask an immediate question, right? What are you trying to integrate with? If I write dx, then your answer minus cos x is right. Had I written it as d theta, answer is only theta. Sin x into theta. Why? So for example, the question had been sin x into d theta. With respect to theta, there is no theta in sin itself. So sin is a constant. Anything constant, you can take out of summation, differentiation, or integration. So that will come out of the integral. Sin x into integral of d theta. That would have been theta sin theta. Are you able to understand? A small change is completely changing the whole things. Right. Correct? So why I told this point is, if I have to integrate and remove the dB, right hand side, I need to know with which variable I'm supposed to integrate. What is the differential coefficient you're able to see on the right hand side? I'm able to see dl, but the question is sin theta related to dl? Is r square related to dl? There could have been two things, okay? I could have integrated with dl, provided I had only dl as a variable and everything else as a constant, like how I did for sin x d theta. Correct? But here what is happening? dl is a variable, accepted. Yeah. Why is dl a variable? Just because you have the d? Because dl means you're differentiating small l. Observe, small l is changing as you change the distance from point O. I never mentioned this is a fixed distance. Correct? What about sin theta? As you keep varying the distance from the current carrying element, the value of r will also change. Why will r change? Because had I taken the current carrying element here, then this would have been my r. Are they both the same? Right? They are not. When that is the case, I need to be careful with that context also. Similarly, if dl and r, the position of dl and r are changing, what is the other parameter that will change? Theta will also change. So what I need to do is, I need to consolidate everything and bring it to a format where I'm able to write everything in terms of one variable. That variable I am free to choose. So I will choose theta as a variable. Means what I'm saying is, I want to write dl in terms of theta I want to write r in terms of theta. That is what I'm going to do. Okay. Having said this, now I'm going to use the basic knowledge. Since trigonometry is involved, what is the first thing your eyes are supposed to look for? You look for a right angle triangle, OAP, or sorry, AOP if I take it, right? If I take this as theta, this as L, okay, generally when you take these triangles, DLs will be ignored. So yeah, if this is theta, this is R. Now tell me what is the relation? What is L divided? So out of L, A and R, which one is a constant always? A is a constant because that is a perpendicular distance. So I will write L in terms of A, R in terms of A, but both related in terms of theta. So if I write L divided by A, what do I call this as? Tan. Vertical by, sorry, opposite by tan illa, cot illa. Just cot theta. Or I will write okay. I'm missing something. Okay. Similarly, what is A divided by R? That is cos theta. Correct? Oh, sorry. Okay. Now, I just want to change a small thing. Okay. I don't want to write things in terms of cot because I'll have a minus sign. I'm not comfortable with it. So, to eliminate it, what I will do is I'll take another angle phi here. Okay. If I take this as phi, now can you tell the same things in terms of phi? Cot theta will be equal to how much? Will be equal to tan phi. And sin theta will be equal to cos phi. Why? Because theta plus phi is 90 degrees. They both are complementary of each other. Right? So L by A is tan phi and A by R is cos phi. So from this, can I say L is equal to A tan phi, guys? But if you look at the first expression that I'm trying to talk about, do I need L or DL? I need DL. So if I need DL from there, then what I will do is differentiate on both the sides. DL will be equal to A secant square phi B phi. This is called chain rule. Right? Let me call this as equation number 2. Is there any doubt? Is there any doubt? DL is equal to A secant square phi D phi. Similarly, what is R equal to? R is equal to A secant phi. I'll take this as 3. Now I'll use this 2 and 3 in 1. If I use it right, observe what is going to happen. dB will be equal to how much, guys? Mu naught I into DL place, I can write it as A secant square phi D phi divided by 4 pi into R square. A square secant square phi. Correct? Can I write it like this? Right. Why I wrote it as A square secant square phi in the denominator? Because R square is there. So A and A are gone, secant square phi and secant square phi are gone. So I have mu naught I divided by 4 pi A into D phi. Now observe this expression. Oh, into sin theta is there. Instead of sin theta, I can write it as sin theta. I will write it as cos phi D phi. Correct? Now see, observe this expression. dB now has it got converted into one variable thing. Mu naught by 4 pi is a constant. I is a constant. A is a constant. Cos phi with respect to phi. You can integrate it. So when I integrate, I need to take proper limits. Observe what I'm going to do. I will take the bottommost points limit as alpha and the topmost points limit as beta. Okay. So mu naught I divided by 4 pi A into cos phi D phi. So B will be equal to integral of mu naught I divided by 4 pi A into what is the limit of phi that we have taken. At the bottom it is alpha, at the top it is beta. So I'll go from top to bottom because that is the direction of my current. So when I go to the bottom right, observe alpha is in anti-clockwise direction and beta is in clockwise direction. So I'll give sign to it. I'll take alpha as negative so that beta becomes positive. So I will take this as minus alpha to beta cos phi d phi. Okay. When I write it like this, then this becomes mu naught I divided by 4 pi A into integral of cos phi d phi is sin phi between minus alpha to beta. Correct? Now substitute the upper limit and the lower limit. So the total magnetic field due to a finite length current carrying conductor will be equal to mu naught I, which is a current, divided by 4 pi into A, where A is what? Perpendicular distance, into sin alpha plus sin beta, or sin beta plus sin alpha, where alpha is the angle at the bottom, angle made by the point P and the bottom. Okay, and beta is how much? The angle made with the top. So if you know these two values, you can solve the problem based on that. Tell me. Because alpha is in anti-clockwise direction. Sorry, anti-clockwise, and beta is in clockwise. It is generally negative, sorry, taken as positive. But here we are free to choose. Because here we are not dealing with quadrants. Sure. Is this enough? They'll give you why do you want to tell. Because it's a generic formula, right? I'm saying phi is a variable, right? I'm asking what is the least value phi can take? Is minus alpha. And the maximum value phi can take is, in the upward direction is beta. So that phi is moving, when it is moving, what is the maximum angle it can take in the downward direction? Minus alpha. Again, when the line is moving, what is the maximum angle it can take in the upward direction? It is beta. So don't worry about it. We'll start with the problem tomorrow.
Sir,
Tell me. Yeah, ma'am.
can you please show the diagram first? Yeah, got it, sir.
Yeah. Is this clear? So this is insert that point. So when you're remembering this formula, right, you should remember that alpha and beta are measured at the end. While doing problem, I'll explain you what are all the points you need to have. We'll start with the problem tomorrow. So apart from that, since this derivation is slightly complicated, I want you all to try it again. Okay, tomorrow's class, first 10 minutes, I want you to, not even 10 minutes, 10 minutes, I want you to write a small test on this and give me the data. Prepare it. Clear? Due to the current carrying conductors, due to state current carrying conductor of finite length. Whole conductor. That is why it is B, it is not dB. That is no possible. It's not 180, it become 90. Minus 90 and plus 90. This is a current carrying conductor. if this is the point P, if this is A, if you call this as minus infinity and this as plus infinity, if I have to draw a point, it will intersect where? Only at infinity. Only parallel lines can intersect at infinity. Alpha is 90, beta is also 90. So there are two types of special cases. One is called as infinite width conductor and second is called as semi-infinite width. I'll go to that concept tomorrow, otherwise you'll get confused. That is the reason I'm saying revise this symptom. Okay, first 10 minutes, I want you to write a test. Those who are online are able to hear me. First 10 minutes will be a test based on this derivation of it. Is it clear? Yes. Okay, so any other doubt? Any other doubts that you have? Clear? Then that's it. Those are online. Any doubts, guys?
No, sir.
Okay.
No, sir.
Good. Okay. That's it, guys.
Thank you, sir.
Yeah. Okay. Wind up.